Hello, everybody. Today we are going to talk about area in polar coordinates. So we've been talking about the calculus of polar. In the video that precedes this one is usually the video on derivatives of polar curves. So hopefully you've done that one too. And so now the other thing that we do with calculus is we talk about derivatives and we talk about integrals. So what do you want to do if you want to find the area of a polar curve? Well, here's the thing. I'm going to kind of slide off to the side here and explain where this formula comes from. So when we do area of like f of x of a curve that's written in rectangular coordinates, the area from a to b is the integral from a to b of f of x dx. Now, why is the area that? It's because technically what we do is we separate this into infinitely many little rectangles, hence rectangular coordinates, and each of these rectangles has a height that's f of x and a base that's an infinitesimally small change in x. So we're really taking the integral of base times height, where base is dx and height is f of x, and then we end up with that. No big deal. Well, when I'm in polar, okay, so let's say I have, I don't know, like a lima bean limousin thing like this, and I want to find the area there. Instead of splitting it up into rectangles, we want to think about that polar grid, that polar graph paper that you've seen before. And instead of me just saying that out loud here, let me actually bring one up. I will go to my favorite place. Hello, Desmos. Hello, old friend. How are you? If I change this over to polar, that's what a polar grid looks like. Okay, this thing right here. And in polar, we get what are called polar rectangles, and that's these kind of things in here. So a polar rectangle is where you take like this little section here. That is what's called a polar rectangle. Fun. What we're going to focus on isn't so much that rectangle, but really this wedge that I just drew. Okay? So if I take some kind of polar curve here, okay, and I separate it into wedges like I just talked about on that other page, I would draw out from the origin and then find the area of this section, and then find the area of that section, that section, that section, and then add all of these together. Okay, so now I need some kind of generic formula for the area of a section that looks like this. Well, if I look at that, I'm going to pull it out and enlarge it. Doesn't that really look like a portion of a circle, right? Where I would know what this angle is, and that's of a piece of a circle. So a piece of a circle has an area of pi r squared. Okay, fine. And if I want a piece of the circle with a radius here and an angle there, the area of a sector of a circle is going to be angle over 360, but 2 pi because we're in calculus, times pi r squared. That would give me the fraction of the circle I want. And well, these will cancel. And so I'd really have the angle divided by 2 times pi r squared. But if I'm talking about calculus and I'm talking about splitting this into infinitely small wedges, instead of having like a big angle measure, I'm going to have an itty bitty angle measure. So calculus wise, we're going to call that d theta, the change in theta from one to the next. This has some kind of change in theta. That has some kind of change in theta. And if I rewrite that, that's going to be 1/2 pi r squared d theta. That'll give me the area of one wedge. I want an area of all the wedges, so I'm just going to add them up. And instead of the integral being from a to b, the integral is going to be from alpha to beta, the angles that sweep out the whole curve. Okay? So let me go back to here and we say, oh, all right, so the area of the region between the origin and the curve, r equals f of theta, for thetas between alpha and beta, is 1/2 r squared d theta. Cool. If your area is bound between two polar curves, you can do 1/2 outer radius squared minus inner radius squared. But I gotta be honest, even though this is technically true, I don't often think about it that way because weirdly, sometimes what you think is the outside isn't the outside. So when I do the area between two polar curves, I really think about it as let's find the area of one thing and then subtract what I don't want separately. Okay, so technically that second equation is true, but I think rather than using that difference formula, we just do things completely independently. But we'll get to that later. All right, so to define the area, you need to determine whether you have one curve or two, and then find the initial and terminal values of your angle. Those become the limits of integration. Okay, cool. So find the area of the dimpled limacon, r equals 3 plus 2 sine theta. So let's go back to Desmos. And I am going to make this r equals 3 plus 2 sine theta. Okay, so there's my dimpled limacon. Now, the nice thing about Desmos is it will trace it out and tell me what my window needs to be. And this is telling me that the period of this graph is 0 to 2 pi. Okay, if you are doing this on a handheld calculator, you would have to kind of test it out and see if your interval is 0 to pi or 0 to 2 pi. So we can talk about those things more in person. But basically, you need to figure out how long does it take to graph this thing. All right, so it takes from 0 to 2 pi to graph this thing. So when I come back here, it's going to be the integral from 0 to 2 pi of 1/2 r squared d theta. And that's it. 1/2 r squared d theta doesn't mean r the letter. It means r the function in terms of theta that you were given. And then we're just going to throw that into a calculator. So let me pull up a calculator here. Now, does your calculator need to be in polar to do polar integrals? The answer is no, but if you would like it to be, by all means. So I'm going to go over here to polar. Radians, degrees, function, polar, all right. And then I'm going to go to y equals 3 plus 2 sine theta, okay. And now let me show you what I mean about graphing this to see how big or how big you need your window. I'm going to zoom 6 this. And there's my dimpled limacon. Now, when you graph in polar on your calculator, your window is going to be kind of garbage because a zoom 6, a standard window, is squashed. So if you go from zoom 6 to zoom square, which is zoom 5, now it looks more like what it's supposed to look like. And another thing I do to see if this curve is graphing correctly is if you go back in here and you change your cursor to, and you change your cursor to the thing that looks like a key, I call that the turtle tracer, it will trace out the graph so you can see where it starts and where it ends from 0 to 2 pi. So now if I hit, I'm going to have to type something else in, so if I type the 3 again, and I graph it, I see that it starts on the x-axis and then goes around and stops. Okay, so now if I want to evaluate this, I can say math 9, 0 to 2 pi of 1/2. Now I'm going to go to alpha trace. And if I go to alpha trace to bring up what would normally be my y values, it's going to bring up r because I'm in polar. 1/2 r squared d theta is 34.5575. 34.5575. And that is the area of this lima bean. Find the area inside the smaller loop of the limacon. R equals 2 cos theta plus 1. All right, so let's graph that. I'm going to do it in Desmos and in my calculator here. So over here, R equals, what was it again? 2 cos theta plus 1. All right. So 2 cos theta, I love that I can type theta as a word, plus 1. Ooh, that's fun. So that's a limacon with a loop in it. Now, if only I knew where that loop started and stopped. Well, if I look on the graph, that loop starts and stops at the origin, which is when r equals 0. Okay, so what I'm going to do is come back over here, I'm going to draw this limacon with the loop. And I need to figure out when r equals 0 because that's going to be when the loop starts and stops. So r equals 2 cos theta plus 1. 2 cos theta plus 1 equals 0 when cos theta equals negative 1/2. And then if I think about when is cosine 1/2, that's at 60 degrees, but I need 60 degrees in the quadrants where cosine is negative. And so that's going to be here and here. So 60 degrees here and 60 degrees there is going to be theta equals 2 pi over 3 and 4 pi over 3. Okay, now just because it's faster to graph in Desmos, I'm going to come back over here to Desmos and I'm going to change my window to make sure I have it right. And I'm going to do 2 pi over 3 and 4 pi over 3 and see if I just get the loop. And I do. Look how cute it is. So I now want to find the area just on that window so I get the area of the little baby loop. So I am going to do the integral from 2 pi over 3 to 4 pi over 3 of 1/2 r squared d theta. And I'm going to do that in this calculator. So 2 cos theta plus 1. Didn't type the theta, did I? Let's try that again. All right. And then I'm just going to go back to my home screen, Math 9, the integral from 2 pi over 3 to 4 pi over 3 of 1/2 r squared d theta. And 0.5435, pardon me. 0.5435. Cool. And that's going to be this little baby area. Yay. All right, find the area of one petal of this rose curve. R equals 2 sine 4 theta, all right? So what does 2 sine 4 theta look like? 2 sine 4 theta, I'm going to graph this here. And when I graph it, all right, I'm realizing I have 8 loops. Now I'm going to do that again here and see where it starts and stops. So when I hit graph, it does start at the origin. So I'm realizing that if I want one petal, I'm just going to say, well, I'm not great at drawing these here. There's one in there, and then there's one there, and one there, and one there. Yeah, good enough. If I want the area of one petal, I'm just going to take 2 pi divided by 8, which is pi over 4, and I know the interval for each petal has a width of pi over 4. So if I want the area of one petal, I'm going to go from 0 to pi over 4 of 1/2 r squared d theta. And so 1/2 r squared d theta, and I just need to change my limits here to 0 and pi over 4. 0.785. Cool. All right. Now it says find the area shaded by the circles r equals 1 and r equals 2 sine theta. All right, so find the area shared, not shaded, shared by the circles r equals 1 and r equals 2 sine theta. All right, so r equals 1 is a circle with a radius of 1, and r equals 2 sine theta. So r equals 1 and 2 sine theta. So there's r equals 1, and there's r equals 2 sine theta. Now I'm going to go back to 2 sine theta and turn the turtle tracer on again. And I'm going to change my window. Theta is going from 0 to 2 pi. I'm fine with that. I want to change this. So I'm going to change my x to go from -6 to 6, and my y to go from -4 to 4. If your y window is 2/3 your x window, you'll basically get a zoom square. So whatever you pick for your x window, 2/3 of that will be your y window. So let me graph that again. There's r equals 1. That goes around once. And there's r equals 2 sine theta. Oh, that goes around twice. All right, so if I want the area shared between them, I kind of want the area of this Venn diagram piece in the center. All right, so I'm going to do this, and I want to find this region right there. Well, how am I going to do that? This is where that second formula comes in that I ignored a little bit. And I did it on purpose because for me, I feel like it makes more sense to do this in a way where I think about each of these graphs independently, because r equals 1 only graphed once from 0 to 2 pi. R equals 2 sine theta graphed twice. So I want to find out somehow how I can find that shaded region. Well, I think no matter what, I need to know what these points are right here. All right, so I want to know when 1 equals 2 sine theta. That's going to be when sine theta equals 1/2. And that's going to be when theta is 30 degrees in quadrants 1 and 2. So that's going to be pi over 6 and 5 pi over 6. So let's see what happens if I change my window to just pi over 6 and 5 pi over 6. So I'm going to go back to my window, change this to pi over 6, change that to 5 pi over 6, and see what happens. Okay, so what happens when I graph that from pi over 6 to 5 pi over 6 is I'm going to get the top part, but what I really wanted was the bottom part. Okay, so this is helpful here. So when we think about it, if I graph that from pi over 6 to 5 pi over 6, I'll get that section out there. Okay, so if I do the integral from pi over 6 to 5 pi over 6 of 1/2 r squared d theta minus the integral from pi over 6 to 5 pi over 6 of 1/2 r squared d theta, I'm going to get this black region out there. Does that make sense? Because I'm doing the area of the outside curve minus the area of the inside curve. Okay, so if I do that, that's going to get me that black section out there. So let me do that real quick. So let's see, which of these did I have in Y1? So 1 and that. So math 9, 5 pi over 6. Nope, that doesn't go there. Still didn't do it right. Oh, Mrs. Vibber, you're making this video take forever because you're typing all this stuff in. I get it. So I am going to, nope, I still can't hit the right buttons today, folks. I am going to do 1/2 the outer radius squared. There we go. And then I'm going to subtract. Ignore the music. You know what? The music's really loud. I'm going to pause this. Son of a gun. Okay, sorry about that. So if we want to evaluate this and find the area of the black section, we were typing some stuff into the calculator. And we did 1/2 r squared d theta, and we were doing 1/2 r squared d theta here, but my second r is just 1, so I'm going to just type 1. And the area of that black section is 1.9132. All right, so I'm going to come back over here, and this is 1.9132. Now, that's the black part. I wanted the blue part. So now I'm going to realize, well, the black plus the blue makes a circle. It makes this circle on top. And if I go back and look at the graph, I realize that that circle on top actually just has an area, it's the area of a circle, pardon me, whose radius is also 1. That red circle that we graphed is a circle with a radius of 1. So the entire region would be pi r squared, and that would give me the area of this entire circle. And then I'm going to subtract that value we just got. So I'm going to go back here and say pi times 1 squared is, pi, minus the answer we just got is 1.228. And that is that area right there. Cool beans. All right, so I know that I'm at like 20 minutes at this point here. I've got one left to do. So if you want, I would like you to pause this video and try and do this one on your own. Just play with it and see what you can make sense of. And then we will meet back up in a second. Because I don't want you to have to sit here watching me type things into the calculator, I'm going to pause my video and then come back when this is done. Okay, we're nearing the end. So on the other screen, I did this last question. Now, my guess is that you kind of got a little bit stuck as you were doing it. So before I even show you the answer, which is 29-ish, by the way, before I even show you the answer, I want to show you what my thought process was in real time. So if I graph this here on Desmos, I have the graph of r equals 2. And I have the graph of, don't look, 3 plus 2 cos theta. R equals 3 plus 2 cos theta. Okay. So I had to figure out where these intersected. So the first thing I did is figure out where they intersect. And you can actually see it here. They intersect at 2 pi over 3 and 4 pi over 3. So if I only graph these things from 2 pi over 3 to 4 pi over 3, what I end up getting, let's see if I do this from, oh, there's no theta in this, so I can't do it. If I only do this section here, it would be this little wedge would be what I get, okay? And the rest of this blue part wouldn't be there. So it would be this blue edge and this green edge, and that's it. And then I thought to myself, well, that's not what I want. I wanted the thing that was way over here. So if I come back and I graph this again from 0 to 2 pi as it should be, what I thought about is that I'm going to split this into 3 regions. Region 1, Region 2, and Region 3. Region 3 is what I want. Region 1 would be the area from 2 pi over 3 to 4 pi over 3. So I said, well, if I can find the area of Region 1 and then subtract that from this circle, then I get the area of Region 2. If I take the whole lima bean and subtract Region 2, I get Region 3, which is what I wanted the whole time. So that is what I ended up doing, is I found out where they intersected, and they intersected at 2 pi over 3 and 4 pi over 3. And I said, okay, if I go from 2 pi over 3 to 4 pi over 3, I would just get this little black wedge. And then I thought and said, I don't want the black wedge. I want the dark part, Region 3 out there, okay? And so I said, well, area 1 would be 1/2 r squared minus r squared, where the outside edge is the circle and the inside edge is the lima bean. 7.4-ish was the area of Region 1. Region 2 is the circle minus Region 1, so pi r squared minus that 7 got me 5-ish. And then Region 3 is the whole lima bean, which would go from 0 to 2 pi, minus Region 2. Long video, hard part at the end. So that, my friends, is how you do polar area. And the long story short is, hope that you only have one region so you don't have to worry about overlapping. But if you do have to worry about overlap, separate your overlapping sections into regions and see what you can get and what you can piece together. With that, my friends, I am out. I hope you are all having a good day and continue to do so.